Hi, I'm Spencer Schroff. My teammates are Nir Mondal and Chris Evagora, and our project is the 2D stair hopper. Okay, this is what our robot looks like. We decided to describe its state as the vertical and horizontal position of the body, the angle of the body, the angle of the leg relative to the body, and the retraction of the leg. Um, our two actuators are torque at the hip and compression of the spring in the leg. Our main goals for the project are to make the robot hop and to find a stair climbing limit cycle for the robot. Okay, so the nice part about hopping robots is that we can separate vertical and horizontal control. Vertical control basically comes down to compressing the spring by a certain amount at the bottom of the hopping cycle, and this will add energy via the spring and get you a higher hop on your next hop. Horizontal control breaks down into placing the foot relative to something called the CG footprint. This is the projection of the center of gravity of the robot on the ground when it's in contact. Um, we do this to control the horizontal velocity and the body angle and regulate the body angle of the robot. When the robot's in contact, we just sweep the foot backwards in time with the velocity of the robot, and it goes according to that equation there. All right. So if you do that right, implement that controller, you get something that looks like this, and you get a nice stable hopping of the robot.
So the next step is to define a limit cycle using trajectory optimization. The uh, the uh, the hard part about finding a limit cycle here is that it is a hybrid model. Uh, the robot is going to be in the air and also in contact with the ground. And in between those two modes, we need to have reset maps um, because in those modes, energy will be lost or velocity might change instantaneously. So the constraints we implemented were dynamics during these modes, uh, the guard functions for the reset maps, uh, also mirror constraints, which basically enforce that the initial states are equal to the final states, which is helpful when uh, building the limit cycle. So once we implemented these constraints, this is the result what we got with the hopper on flat ground. So in the graph below, you can see we've plotted the z state space, and the blue curves represent the two modes, and the red dashed lines represent the reset maps. And then in the right, you can see that the initial state is very similar to the final state, except for that x offset. Next, we had the robot climb upstairs, and it was able to do that. Once again, you can see the graph of the state space is very similar, except now we have a z height offset. And once again, the initial state and final state are very similar as well. One issue we ran into when setting up the program for trajectory optimization was that when we were implementing the equations of motion using manipulator equations, we were getting infeasible constraints. So what we did was to make the dynamics more simple by implementing them explicitly. So for example, constraining the z acceleration of the robot to be negative g. One thing we might want to do in the future is have more sophisticated dynamics, particularly for the contact phase, uh, and also perhaps add cost to leg torque uh, to optimize for less torque.